Hi, welcome to the screencast for 18.3. I'm going to try and move through this quickly so I can do this in just one screencast. And when we start out looking at 18.3, we're looking at the idea that water can fall apart all by itself. It doesn't have to have an acid or a base in it to fall apart. And when just pure water falls apart, you're going to get one H plus ion and one OH minus ion. And it's going to have an equilibrium value just like the acids and bases do, but instead of calling it Ka or Kb, we're going to call it Kw since it's water and it's neutral. But it's going to be calculated the same way with products over reactants. In this case, our products are hydrogen ion and hydroxide ion over the reactant, which is water. And since water has a known concentration or density of 1 gram per milliliter, you can really just leave the water out because anything divided by 1 is itself. So we end up with the Kw equal to H plus times OH minus. And at 298, scientists have found that this value is 1 times 10 to the minus 14th. And this means two things. First of all, it means that very little water actually falls apart without an acid or base added to it, because 1 times 10 to the minus 14th is a really, really small number, a lot less than 1. But it also means it's an inverse relationship. So if you increase the hydroxide ion, then the hydrogen ion is going to decrease. Or if you increase the hydrogen ion, the hydroxide ion should decrease. For example, if you have a cup of coffee and it's got an H plus concentration of 1 times 10 to the minus 5th, that means that the H plus has increased, so the OH minus should decrease. And we can prove that that's true because we know that the Kw should equal 1 times 10 to the minus 14th. And we know that that 1 times 10 to the minus 14th has to be equal to the H plus. Let me rewrite this. This has to be equal to the hydrogen ion times the hydroxide ion. So when I plug in numbers, Kw is always 1 times 10 to the minus 14th. And now I have 1 times 10 to the minus 5th. And I'm trying to find out my value for OH minus. So if I move my 1 times 10 to the minus 5th to the other side by dividing both sides, you can either do this on your calculator or in your head. But either way, you should come up with an OH minus concentration of 1 times 10 to the minus 9th. So the OH did go down as the H plus went up. And they still give you a product of 1 times 10 to the minus 14th. So if we look at this next couple slides, what we learned in chapter 17 from Le Chatelier really explains why this should happen, because looking at our balanced equation and our equilibrium equation for water, if you add, in this case I put, if you add H plus ions, you're really adding a product, and that means that those H plus ions are going to drive the reaction left as they combine with OH minus ions to form new water, which means as your H plus gets increased or gets added, your OH ions are going to get used up or decrease. And just the opposite will happen then if you added base or OH minus ions. These new OH ions would combine with H plus ions already there. So hydrogen ions would decrease while OH ions, increase, and your product remains constant again. Another thing we can find from this value of 1 times 10 to the minus 14th is it lets us know how much H plus and OH minus we have in water or a neutral solution, because H plus times OH minus has to equal 1 times 10 to the minus 14th, and we know that we get 1 hydrogen ion for every hydroxide ion because water is really HOH. So we could just divide the 1 times 10 to the minus 14th in half, and half should be H plus and half should be OH minus. And so that means each one should have a value of 1 times 10 to the minus 7th in a neutral solution, and their product should be 1 times 10 to the minus 14th. Now, if you remember anything at all about pH, which you may or may not, pH is a value between 0 and 14, and neutral substances have a pH of 7. And 7 and 14 should ring a bell because we just saw them as our exponents. And it's no accident. If we take a look, the pH scale is always a product of the H plus and the OH, or the product of the OH and H plus is always somewhere between 10 to the 0 and 10 to the minus 14th for each one's concentration. So these are really small numbers with negative exponents. So scientists just simplified this math and said if we took the negative logarithm of the hydrogen ion, we would get this manageable positive number between 0 and 14, which would be a lot less confusing. So that's what they've done. Basically what you're doing is you're taking the exponent, getting rid of the 10, just taking the exponent and taking the negative value of it. So pH less than 7 is going to mean there's more H plus ions, or it's acidic. And a pH less than 7 is going to mean you have fewer H plus ions and more OH, and it's basic. And of course, if it's a pH of 7, you've got equal numbers of both H plus and OH minus. So how do you find the pH of these 4 items? You take the negative log of whatever your concentration is. This is 1 times 10 to the minus 8th. And you plug it into your calculator just like that. Use your negative button, log. Plug in the value given. Make sure you close your parentheses. And you end up with 8. If you do the same thing for the others, you might want to pause it here and go ahead and try. But the pH for the second one is going to be 4.5. The pH for this one, since it's 2 times 10 to the minus 11th, it's not going to be quite minus 11th, but it's going to be 10.7. And the last one's going to be about 2.7. So again, looking at those, the 8 means it's slightly basic. 4.5 is slightly acidic. 10.7 is fairly basic. And 2.7 is fairly acidic. The other thing to keep in mind with the pH scale is because we've brought the exponent down, we've taken the negative log of the exponent. When you go from a pH of 6 to 4, you don't have 2 times as strong an acid. You actually have 10 times 10 as strong an acid, because this is 2 pH units, and 1 unit of pH is a 10 times change. So if you change it twice, you have to take 10 times 10, or a change of 100. And you could prove this to yourself by changing your pH back into the concentration. Would have 1 times 10 to the minus 6th, decreasing to 1 times 10 to the minus 4th. And if you take the stronger one, 1 times 10 to the minus 4th, and divide by 1 times 10 to the minus 6th, you're also going to see it's 100 times change in concentration, or a pH of 6 is 100 times weaker than a pH of 4. Sometimes scientists are dealing a lot more with bases, or what we call alkalines, alkalinity. This is especially true with soil science, agriculture. They're a lot more interested in alkalinity. So they tend to use the pOH scale, and the pOH scale is set up the same way as pH, but now you use the negative log of your hydroxide ion. And the sum of your pH and pOH is going to have to equal 14, and that's because you're taking the exponent of your hydrogen concentration and the exponent of your hydroxide concentration, and we know those two exponents have to add up to a negative 14, or 10 to the negative 14th. So that means the negative log of those would also have to end up to 14. So if you were told you had an antacid solution with a hydroxide ion concentration of 3.2 times 10 to the minus 5th, you could calculate both the pH and the pOH. I could find the pH by taking the negative log of 3.2 times 10 to the minus 5th, and I come up with a pH. Let me just write what I'm doing here. Negative log of 3.2 times 10 to the minus 5th, and I come up with a pH of 4.5. My pOH then has to be equal to 14 minus this 4.5 because they have to add up. So my pOH should be 9.5, so that my pH and pOH give me a total of 14. A slightly more complicated version of this is if you have the hydrogen ion concentration of a soft drink at 8.3 times 10 to the minus 4th, what is the pOH and what is the concentration of OH in the solution? So I could do this a couple of ways. I could take the negative log of the H plus, 8 times 10 to the minus 4th, and that would give me a value of 8.3 times 10 to the negative 4th. getting a value of 3.1. And when I do that, I can then take 14 minus 3.1, and I get a value of 10.9 for my pOH. Because remember, this is my pH since it was a hydrogen. So now I know my pOH, but I still need to know my hydroxide concentration. And I can do this two different ways. I know that Kw equals H plus times OH minus. And I know that Kw has a value of 1 times 10 to the minus 14th. I know that the H is 8.3 times 10 to the minus 4th times the OH. So if I get the OH alone and take my 1 times 10 to the minus 14th and divide by the 8.3 times 10 to the negative 4th. Let me just pause as I put this in. So I divide these, I end up with a value of 1.2 times 10 to the minus 11th as my OH concentration. But if I didn't have all this information, if all I knew was the pOH, I could still find my OH concentration, because pOH is equal to the negative log of OH ions. And I know that my pOH is 10.9, so I can undo this. This is really was 10 to the minus 10.9, or you can use the anti-log or second log on your calculator to do this. But when I plug in 10 to the minus 10.9, I get very close to the same answer. This comes out to 1.26 times 10 to the minus 11th. So we can either find pOH from the concentration, or we can find the concentration from the pH or pOH. The last thing to finish up on here is just how do we measure pH experimentally? And we're going to be doing this in class. We're going to be doing a lab using pH probes. But there's a couple ways to do it. You could do it like we did in the launch lab and just get a qualitative idea if you have an acid or base by using some kind of indicator like litmus or pH paper. You can also use a conductivity tester, although that doesn't tell you if it's an acid or a base. So usually use some kind of indicator. It's a chemical and will change color when you dip it in the solution. It can also be made from a liquid, like cabbage juice is one. Otherwise, pH meter is the way to get an actual quantitative number. And a pH meter, your book describes how it conducts the electricity and changes that into a readout that the more conductive it is, the lower the pH for an acid, or the higher the pH for a base. And that's it for 18.3.